Hello, everybody. I hope you are doing well. Today, we will discuss the benefits of nuclear magnetic resonance logging tool over the other conventional logging tools for the purpose of hydrocarbon exploration. With the invention of NMR logging tools that use permanent magnets and pulsed radio frequencies, the application of sophisticated laboratory techniques to determine formation properties in situ become now possible, and this capability will open a new era in formation evaluation and core analysis. Let's start by a little introduction about the basic physical principle behind the NMR physics. The basic principle is the nuclear spin. Each nucleus will spin around its axis, and its axis will in turn also make some rotation around a certain axis of magnetic field. And this spin or the spin around the axis will produce some weak magnetic field from the nucleus. Basically, we have, if for example, we consider the hydrogen nuclei existing within the fluid of the pore spaces, we will have at first some random distribution of the spin of hydrogen nuclei around the axis. There will be some random distribution of the spinning protons or spinning hydrogen nuclei. And due to this random spin, there will be some cancellation between the opposite spins. And so the magnetic field will be tending to be zero. This is in the absence of any magnetic field. And so we have first to apply a very strong magnetic field or some very strong magnetic field to make some polarization of the hydrogen nuclei to be having some larger numbers spinning parallel to the applying polarizing field, and some minor photons spinning in the anti-parallel direction, and so there will be some observable or measurable magnetization caused by the difference between the signal or the magnetic field produced by the parallel photons and the anti-parallel ones. So the first step will include applying some polarizing field. This polarizing field will make some alignment or larger alignment of protons to be some large number of spinning protons spinning parallel to the applied polarizing field, and some minor number of protons spinning anti-parallel to the applying magnetic field. And so it will change the state of protons from being randomly spinning protons into somewhat aligned protons. And so there will be some increase of magnetization with the time. As the time progresses, the number of protons that will spin in the direction of the polarizing magnetic field will increase, and so there will be some increase in magnetization until some saturation limit here or some maximum magnetization here, and this will produce some exponential curve. This exponential curve or exponential polarization curve will have a time constant called T1. T1 is called the longitudinal relaxation time. So this is the first step, is to polarize the randomly distributed or randomly spinning proton nuclei within the fluids existing in the pore space. The second step is to apply some sequence of radio frequency pulses. And these radio frequency pulses will exert some alternating magnetic field on the protons that will tend to make some tipping of the direction of the spin of protons into the new direction of the pulse creating this phenomenon. And so we will apply, for example, a 90-degree pulse that will tip the proton from the vertical, from spinning in the vertical direction into spinning with an angle of 90 degrees here. And then we will apply some sequence of pulses with 180 degrees that will tip or change the spinning of proton in the reverse direction. And as we apply this sequence of pulses, for each pulse, there will be some on and off. When we start the pulse on, there will be some increase of the number of protons spinning in the same direction of the alternating magnetic field caused by this pulse. And then when the pulse is turned off, there will be some decrease of or decay of the number of protons spinning in this direction. Another pulse, or 180-degree pulse, will create some increase of the magnetization, and then when we turn it off, there will be some decrease of magnetization, and so on. This will be produce some sequence of what is called echoes. So these are a sequence of echoes, and this sequence of echoes will be of decreasing amplitude, and the curve that will connect all of these decreasing amplitude is called the free induction decay curve. It is an exponential curve characterized by another time constant called T2, or the transverse relaxation time. T2 or the transverse relaxation time. The third step in NMR logging is to apply a wait time for recovery of hydrogen magnetization, and then to repeat applying the polarization again and the applying of the sequence of radio frequency pulses again. So this is the basic sequence of stages for NMR acquisition. So finally, we can get the raw data here as being two time constants. From the polarization stage, we have increase of the magnetization with time, and this produces exponential curve with a time constant called T1, or the longitudinal relaxation time T1. While for applying the radio frequency signals or pulses, starting by the 90-degree pulse and then 180-degree pulses, there will be some production or producing the echoes of decreasing amplitude, and they will produce some another exponential curve with a time constant called T2, or transverse relaxation time T2. The distance between the successive pulses will be called the T echo or TE here, which is the T echo here. So these are the two characteristics time constants obtained by the NMR here. And you can see the sequence of stages starting by polarization, and then recording the T1, and then tipping and free induction decay, and measurement of T2. This sequence of pulses starting by the 90 degree and then 180 degree and sequence of 180 degree, it is called the CBMG sequence. This sequence of pulses is called CBMG sequence. Also, you can see some summary of the stages for NMR position, starting by polarization step. This is the polarization step here with a time constant T1, and then the free induction decay with a time constant T2. Also, the distance between successive passes here is T echo. Another polarization after waiting time, we make another polarization and some free induction decay, and the waiting time will be the distance in time, the time between the end of the decay, the free induction decay of the previous sequence and the start of the free induction decay for the next one. And you can see here illustration of the sequence, the CBMG sequence. We have two CBMG sequences here applied here for the same at the same depth station. And about the effect of the pore size on the value of the relaxation time. As we have larger pore space, we will have some short time diffusion limit. And as we have some small pore space, we will have some long time diffusion limit here. This is about the diffusion limit. You can see in the case of the different pore sizes, you can see the effect on the relaxation time by the following illustration. You can see for large pore size, we have some long relaxation time here, while for medium relaxation, for medium pore size, we have some medium relaxation time. And for small pore size, we have a very short relaxation time. And the NMR signal for a real pore will be a mix or a mixture for the signals from all pore sizes within this pore sample. Let's now see some presentation about the compensated magnetic resonance logging tool by Schlumberger, and another tool, the magnetic resonance induction logging tool by Halliburton. Let's start by compensated magnetic resonance tool by Schlumberger. Let's move now to the magnetic resonance induction logging tool by Halliburton. And this is logging one of the families of logging while drilling. The magnetic resonance induction logging tool while drilling. You can see the tipping of photons due to the radio frequency pulses here. And this is the use of G1 data for formation evaluation model. Differentiation between the different fluids. Now let's discuss some important characteristics of magnetic resonance induction logging tools. First, the signal used to create each image come from a well-defined location within the formation, typically a thin slice or cross-section of the target. And because of the physical principles underlying nuclear magnetic resonance technology, each image will be sharp, containing only information from imaged cross-section, with the material in front or behind being essentially invisible to the NMR. And second, only fluids will be visible to NMR, while matrix or solids will produce a signal that typically decays too fast to be recorded. And so these NMR principles can be used to analyze the fluids held in two spaces of reservoir rocks. The basic component, let's discuss the basic components of nuclear magnetic resonance imaging logging tool. At the center, we will have the permanent polarizing magnet, which produces a strong magnetic field to polarize the hydrogen nuclei. And second component will be an antenna surrounding this magnet, and this antenna will transmit the radio frequency pulses into the formation, and also between these pulses, the antenna will be used to listen for the decaying echo signal from those hydrogen protons that are in resonance with the field from the magnet. And because of the linear relation between the proton resonance frequency and the strength of a magnetic field, the frequency of transmitted and received energy can be tuned to investigate a cylindrical regions at different diameters around the magnetic resonance imaging tool. So by increasing, for example, increasing the frequency, we can investigate the more shallow region or more shallow slice, while for decreasing the frequency, we will obtain the higher wavelengths, and so we can investigate the more deeper thin slice. The magnetic resonance induction logging tool can be operated for Halliburton. It operates at 9 separate frequencies. So we can cover 9 thin slices with different depths of investigation within the formation. And the use of multiple frequencies allows independent information to be obtained from multiple concentric cylinders, about 9 cylinders, by improving the signal-to-noise ratio and enabling faster logging speeds and permitting different pass timing sequences for complex data acquisition. And about comparing the NMR tool with the other conventional logging tool. For example, by comparing NMR tool to the other conventional porosity logging tool, neutron bulk density, and acoustic or sonic, We all know that this conventional porosity logging tool will respond to all components of a reservoir rock, so they are also affected by the matrix. And so these conventional tools tend to be much more sensitive to the matrix material than the pool fluid. While for NMR, it is not affected by matrix, since there will be a very large or very fast decay of the signal coming from hydrogen using the structure of matrix or structure of the matrix of the rock. And so the matrix for NMR will be inversed. By comparing NMR to the conventional resistivity logging tools, while being extremely sensitive to fluid field space and traditionally being used to estimate the amount of water present in reservoir rock, cannot be regarded as true fluid logging devices. The resistivity tools are strongly influenced by the presence of conductive minerals, and also for the responses of these tools to be properly interpreted, there will be some need for detailed knowledge of properties of both of formation and water in pore space. The magnetic resonance induction logging tool can produce three basic types of category of information categories. The first information category will be information about the quantities of fluids in the rock. The second information category is the information about the properties of these fluids and discrimination between them. The third category is information about the sizes and distribution of pores that contain these fluids. And let's move to some important also characteristic of the T2 distribution is the use of cutoff of the T2 distribution to discriminate between the different types of fluids here. So, for example, we have the total area under the T2 distribution will represent the total porosity here, while for the area below the distribution to the cutoff of 3 milliseconds, this area will represent only the clay pond water volume, while the area below the distribution between the cutoff 3 milliseconds and the cutoff of 33 milliseconds for the case of sandstone, while 92 milliseconds for the case of carbonate. This area below this T2 distribution between these limits will be the bulk volume reducible here, while the area below the T2 distribution under the interval of cutoff of 33 milliseconds for the case of sandstone or 92 milliseconds for the case of carbonate, extending to larger values of T2, this area will represent the movable fluids or the volume of movable fluids. So we have these movable fluids, including both of movable water and hydrocarbons, while for the BVI or the area here will represent the water attracted to the small pores by capillary forces, while for the CBW or clay pond water, it is representing the water attracted to the electrical charges on the silicate structures of clay minerals here. So phi effective can be estimated from the area between the intervals or the cutoff of the this cutoff of including both of capillary pond water and the movable water. This will represent the phi effective here, while phi total will represent the total area below the T2 distribution here. This curve is the result of applying mathematical inversion to the raw data of T2. As you see, this is the raw data of T2, including the echo amplitude, and this is the decrease of the echo amplitude, as you will see. And by mathematical inversion, we can get the NMR positive versus time, and from it we can interpret it to obtain the different types here of fluid. So from the cutoff, we can obtain estimates of the volume of clay pond water, volume of capillary pond water, and the producible fluids. This is about the use of T2 distribution, and we can obtain water field porosity both of total and effective porosity, and also we can obtain some discrimination between fluid properties, and we can obtain from NMR some information about the viscosity of different fluids we have. And this is because magnetic resonance induction logging 2 can be run with specific path sequence setting or activations that enhances the ability to detect particular fluid conditions. Also about pore size and porosity, we have some relation between the pore size and the relaxation time. As we have larger pore size, we have larger relaxation time here, and as we have more shorter pore size, more smaller pore size, we will have some smaller relaxation time. And for the purpose of pore or pore NMR, the NMR signal from a real pore will be a mix of the signals coming from all the pore sizes, including in this pore sample. So let's see also some illustration about the use of NMR for the purpose of permeability estimation. As you will see, we have here two samples. The two samples are of relatively similar porosity, or they are approximately of the same porosity. The first sample of porosity 20%, second sample is of porosity 19.5%. While there is a greatest change of permeability. For the first sample, we have 7.5 millidarcy. For the second sample, permeability equal to 279 millidarcy. As you see from the T2 distribution, for the first sample, we have most of the area of the curve is toward the right, while for the second sample, we have some more shift. Sorry, for the first sample, we have most of the area is toward the left, while for the second sample, we have more of the area is shifting towards the right into the larger relaxation times, into the area of producible fluids, of the cutoff for producible or movable fluids. So as we will have a shift toward the larger relaxation time or towards the right, we will have more or larger permeability. As we will have more shift towards the left, we will have more capillary water and more reducible water, and so we will have less permeability here. So also we have two models for estimation of permeability from NMR measurements. The first model is the Schlumberger model of the T2 mean, which uses the logarithmic mean of the T2 distribution, in which we can estimate the permeability as equal to a constant multiplied by the logarithmic mean of the T2 distribution square multiplied by phi or positive is to the power of 4. The second model or second equation is called our free fluid model, which uses the ratio of free fluid volume to the pond fluid volume, and so permeability will be equal to the porosity subdivided by constant C to the power of 2 multiplied by the free water volume or subdivided by the bulk volume irreducible to the power of 2 here. And about the compensated magnetic resonance logging tool by Schlumberger, there will be two basic measurements, the CMR porosity and the T2 logarithmic mean. And we can obtain some calculation of the free fluid porosity, phi effective, and the permeability K. Here is another illustration about the cutoff and the discrimination of the different types of fluid, the capillary and the clay pond water and the capillary and the movable water. We have from CMR, we have three types of porosity. The total CMR porosity, which is the total area below the T2 distribution. The 3 millisecond CMR porosity extending from the 3 millisecond cutoff to the right. This area under the curve will represent the CMR P3 millisecond. The third porosity data will be the CMR free fluid porosity, which extending from 33 millisecond to above. And these values for cutoff is used only for sand and will be changed for the case of carbonate. As you will see also, you can see some relation between the displacement of the T2 distribution and the amount of the clay pond water and the capillary pond water. So here at the bottom, we have more of the T2 distribution towards the left. And so we have larger values of clay pond water and the capillary pond water. The yellow here representing capillary pond water and the brown representing the clay pond water. While in this zone or this depth interval, we have some shift toward the right, and so we have some less amount of capillary pond water and clay pond water. And about the versions also of CMR and about is another illustration. You can see here in this zone we have more of the T2 distribution toward the smaller value of T2, and so we have larger amount of clay pond water and capillary pond water. While here we have some more shift toward the larger relaxation time towards the right, and so we have less values of clay pond water and capillary pond water, and so there will be some less value of shale here. Also, there will be different versions of CMR. There is some CMR plus, CMR 200. These are different versions of CMR. Also about some illustration about CMR versus conventional cool. The CMR will provide a good correlation with the permeability obtained from conventional cool analysis. So there will be some good correlation between permeability obtained from CMR or in general NMR logging tools and the permeability obtained from cool samples. Another illustration here, and as you can see here, we have some displacement of the T2 distribution toward smaller relaxation time, and so there will be some larger amount of clay volume here, while at the top we have more displacement into the larger relaxation time, so we have a less amount of clay and more of sand counts here in this zone. Also, it is illustrated here at the bottom of this log. We have large amount of clay, and so there will be some shift towards a smaller relaxation time due to the increase of clay pond water and the capillary pond water. Another illustration, and this illustration about the gas detection. You can see from the top here, we have most of the curve is toward the smaller relaxation time. So this is indicating high reducible water saturation. And so this will be corresponding, as you can see, this is corresponding to high gamma ray, which indicates a larger amount of clay here. While moving toward the middle, we have more shifting of the T2 distribution into the larger relaxation time. And so there will be some, this is accompanied by some decrease of the gamma ray as shield indicator, and so we are moving into less amount of clay volume here. But when comparing between the NMR porosity and the neutron porosity and the density porosity, you can see at this zone some separation between the NMR porosity and the density estimated porosity. And this is because the total CMR porosity doesn't depend on matrix. It can be used with the density to identify gas in cherry zone by the separation between NMR porosity and the density porosity here. And as a summary of the CMR applications, for obtaining lithology independent porosity, and this is used for evaluation of direct porosity without the need of correction for lithology as done by neutron or other conventional logging tools which need some correction for lithology. The second use for estimation of free fluid porosity or effective porosity, and this is used for reserve calculation. The third use is determination of reducible water saturation, and this is used in the prediction of water cut values. The fourth use is in the identification of permeability, and this is used for the evaluation of producibility of the reservoir. The fifth use is for obtaining pore size distribution, and this is to evaluate the reservoir quality. The gas detection, bitumen identification, plugging, which is used in evaluating the producibility of reservoir, tar sand analysis, which is used in evaluation and research. Thank you so much, and to get more about the presentation, please subscribe and write down your mail here. Have a good time.